And it's finally time for us to take a closer look at the periodic table. And we're going to pair this with compound formation because you'll see some relationships as we go through this. The periodic table of elements organizes all of the elements by properties. It ends up being physical and chemical properties. And there is a bunch of really interesting history about how we ended up with this modern version of the periodic table. I'll try to find some kind of sidebar stuff if you find that you're really interested in that. Where we're going to focus is what's there now, how do we use it, and how can it be a helpful resource? There is something that we call the periodic law, and it is the same basis of what we just described about how the periodic table is put together. And it's that the properties of the elements are periodic functions of the atomic numbers. So you will find that things are grouped with, and we'll really formally define that word group, things that have similar properties. So the reason that the periodic table is as wide as it is because that things in the same columns have similar properties. So like periodically, in a very predictable way, properties appear for different chemicals. And so that's why they ended up where they are. When you look at an entry in the periodic table, so I have phosphorus here as an example, you will see the symbol, so P for phosphorus. If the periodic table is big enough, you'll see the name. So I have the name written here. Sometimes the name is left off because you can always look up the name based on the symbol. You will see the atomic number. So for phosphorus, that's 15. It might be over to the left. It might be directly above the phosphorus. That is the number of protons. And the things in the periodic table are arranged by the number of protons. So to the left of phosphorus, you will find silicon, which has 14 protons. And to the right of phosphorus, you'll find sulfur, which has 16 protons. The other thing that you'll see is the atomic weight. I know I've referred to there being an atomic weight in the periodic table when we were looking at weighted averages. This weight that's listed will be the weighted average. So when you look for fluorine, that's the only element for which the isotope that you see listed is the atomic mass of that one isotope. Everything else will be a weighted average. I've got an image here from ptable.com. This periodic table is linked in the learning management system. It's an amazing periodic table. It's incredibly useful. It's also really easy to get to online. You can link out to a bunch of different information. My only caveat is that this is not the exact periodic table that you'll be using when you take an exam or a quiz. So don't forget to look at the periodic table that's also provided in your equation sheet. In the periodic table, you'll see a bunch of things listed. So we have columns that are groups, and then the rows are called periods. The columns or groups are all labeled with numbers. Now, in this periodic table, it goes from 1 through 18, which is extremely logical. Makes so much sense, right? There should be nothing controversial about this. However, these are new number labels for the groups. And by new, I mean in the 1990s. So literally decades ago at this point. However, when you look at some older periodic tables, which are still in all of our classrooms and prevalent on the internet, you might see some old labels. So they have Roman numerals, they have A's and B's. Those numbers can be useful for some quick tips and tricks that, depending on your chemistry background, you may have used before. But the formal, appropriate, and up-to-date column labels are just 1 through 18. We do have names for some of the specific columns, And you'll see that a couple of them are listed here. Not all of them are listed here. So some examples that are not listed. So column 1 is usually, not counting hydrogen, the alkali metals. And column 2 is usually the alkaline earth metals. Now, it's kind of labeled in this key in the middle, um, but on the right-hand side of the periodic table, the key just says other nonmetals, but we do have columns 15, 16, and 17 that have some special names listed. For the most part, I think only halogens is going to come up in this class as a name that we use. I don't know many people in general who use the pnictogens or chalcogens as a way of referring to those columns, but calling the things in column 17 halogens is incredibly common. Okay, so periodic table, everything's in order by the number of protons. The things that are in columns together will have similar properties, and that's kind of like why we are able to name them, right? We can call something a halogen, and eventually, once you've built up all of this knowledge, you'll say, oh, okay, if you're calling this a halogen, it means these things about that element. You'll also notice that there's a little bit of a weird spot. The 57 through 71, around row 6, and the 89 to 103 in row 7, there's like a call out or like a separated section. Now, this is like a very normal format for the periodic table where we have this cute little castle block and then we have the 2 rows underneath. Those 2 rows underneath are the lanthanides and actinides. Now, they're separate from the periodic table, but based on the numbers, right, if we were to put them in the appropriate place so that everything is ordered by the number of protons, they would show up in rows 6 and 7, and that's where they really belong. So if you go to ptable.com, if you go to the upper right corner, there's a box that you can check to give you the wide version of the periodic table that will put these in the correct place. And the only reason that we don't normally show them in the correct place is that they are elements that we don't use very commonly. They're super interesting. They do really cool chemistry, but we don't use them. So we're like, if I pull this out and put it at the bottom, I can print this on a regular piece of paper. It's just, it would be difficult to work with if they were in their proper place, and we don't use them that often. So we've sort of like footnoted them. I don't know, unfairly, fairly, you decide. I'll let you decide on that one. So that's the only reason that the periodic table has that little section at the bottom, even though it does fit in the middle of that big block. So a recap, we have said this, elements in the same column or group have similar properties. And because of this, we see trends in how they make compounds and ions. So the compounds and ions, this is the stuff that, right, when I call something a halogen, you're going to say, oh, okay, that means it likes to make this kind of ion. So that's the first example. Halogens form -1 anions. So you will not see a cation for a halogen, and you will not see a -2 anion for a halogen. You will only see a -1 anion. So that means that fluorine would form F-, chlorine would form Cl-, Br-, I-, right? I'm just going down the column of the halogens. The alkali metals, so the things in the first column, form +1 cations. So that means that you will not see an alkali metal with a 2+ charge, and you won't see an alkali metal with a negative charge. They're going to form +1 cations. So lithium 1+, sodium 1+, potassium 1+. You'll also see some trends in compound formation. So things like nitrogen and oxygen really like to bond to each other. Now they're in separate groups, right? They're right next to each other in the periodic table. So we wouldn't say that they have similar properties, but the two bonding together happens pretty readily, and we see different combinations. So this is kind of a showing that it is possible to get different combinations when you put these things together. So nitrogen and oxygen, you might see it as one nitrogen, one oxygen, one nitrogen, two oxygens, two nitrogens, four oxygens, or two nitrogens and five oxygens. Just know that there are a bunch of options there.